question into a consumer AI, you get a seamless, instant answer. But when that exact same technology hits the reality of a highly regulated defense or aerospace environment, it shatters. This diagram illustrates why. Deploying AI in the enterprise fails because organizations hit a simultaneous five-front bottleneck. First, your data is trapped in isolated systems, from engineering product lifecycle tools to standard email inboxes. Second, the clock is ticking on all of that data. It evolves continuously, meaning a static answer pulled from yesterday's files can be completely wrong today. Third, generic AI models have a total lack of domain context. They don't inherently understand 3D geometry or bills of materials. And fourth, processing those massive, complex datasets at scale causes your token cost to explode. Finally, you have absolute data protection mandates. The intelligence you generate can never leave the building. Solving this requires a deterministic state machine. That is exactly what kiLM, Knowledge and Intelligence Lifecycle Management, is built to do. Addressing these 5 constraints simultaneously requires a native architecture that manages the entire lifecycle of intelligence, from the moment data is ingested to the moment it is cited in a report. The first step is handling the intake. kiLM relies on a temporal workflow engine capable of parsing up to 48 complex formats, pulling in everything from raw 3D CAD geometry to rigid relational databases. This engine intercepts that chaotic web of federated silos right at the point of entry. It normalizes all of those different languages into a single format that a machine can actually query mathematically. But having the data isn't enough if the data is stale. Quoting an engineering change order from yesterday can result in a massive compliance violation today. This network graph shows how kiLM's bitemporal knowledge graph solves the freshness problem. Every extracted piece of intelligence is assigned a valid from and valid to timestamp. When a file is updated, the old node is instantly marked as superseded. During a search, the system actively filters out those superseded chunks. The query pulse bypasses the expired nodes entirely, forcing the AI to draw its answers exclusively from current truths. By controlling the exact temporality of ingestion, the system grounds the retrieval layer in the latest valid facts, ensuring the AI never draws from an expired or superseded source. Standard language models are essentially predicting the next word. They cannot read a proprietary bill of materials and understand the physical relationship between a chassis and the bolt. To bridge that gap, kiLM uses a semantic partition framework to divide enterprise knowledge into distinct, secure domains, isolating compliance data from engineering data and enterprise operations. This diagram illustrates how graph neural networks process that partitioned information. The raw, unstructured text on the left is mapped into a structured, hierarchical 3D tree on the right, known as the master ontology. This teaches the AI the actual physics and rules of the business. It allows the system to run a forward pass through the graph, predicting exactly what happens to a subassembly if a single upstream component fails. Contextual intelligence requires a structural map of your company's reality. Relying on text retrieval alone will always fall short for complex engineering decisions. Even with perfect context, routing millions of daily enterprise data transactions through massive generalized AI models is financially impossible. This central routing hub represents the task-aware LLM router. It acts as the system's token budgeting core, intelligently splitting the flow of incoming queries based on exactly what kind of brainpower is required. Basic tasks like entity extraction are routed down the classical NLP fast path. It operates up to 1,000 times faster and costs fractions of a penny, reserving the heavy, local LLMs exclusively for complex reasoning. Then there is the ultimate deal breaker for industrial giants: data protection. For defense and aerospace, completely offline, air-gapped operation isn't optional. kiLM enforces strict ACL mirroring. If an engineer doesn't have the permission to open a specific file in SharePoint, the AI will mathematically refuse to surface, read, or summarize that file in the chat. By right-sizing the compute at the router level and strictly mirroring source permissions, an enterprise can scale intelligence across its entire workforce without exposing a single piece of IP to the open internet. All of these layers converge in the user's hands at the engineering knowledge workbench. Let's say an engineer prompts the system to determine the impact of replacing a single, specific component on a legacy product line. In microseconds, the system pulls from the federated lake, actively filters out superseded change orders, applies the graph neural network to understand the physical context, and routes the processing locally to manage costs. The output is a highly specific, permission-locked answer. It is backed by direct, auditable citations, and it is delivered entirely behind the safety of the corporate firewall. Scaling intelligence across the organization depends on this underlying governance. By solving for these 5 specific constraints, the paradox of regulated AI becomes a manageable, auditable part of the daily engineering workflow.